Hey there, in this lecture, I'm going to break some new ground. I'm going to begin talking about quantum mechanics and how that can be described in pi space. Now, the, the, the pi shells can be characterized as either being a particle, an atom, or even a planet. And I've explained in previous lectures, if you've followed them, that when something moves faster, it gets smaller. We call that shrinkage velocity in the Newtonian terminology. And uh, in the 20th century, Louis de Broglie won a Nobel Award for showing that a particle which moves and has momentum has a particular wavelength. So let's just take a look at how we visualize that in pi space. So what you have is an object, you have an observer, and then you have an object moving relative to an observer, and it has what we would call momentum, and then that momentum is characterized by p, and the relativistic version is as follows. So we multiply it by the Lorentz transformation. So we move on to the next and slightly more complete diagram, which is that according to this idea, you can shrink in pi space. You can keep accelerating something up to the speed of light, and what that actually means in pi space is it gets smaller and smaller and smaller. It goes down to the quantum size, the atom. So the atom shrinks, particle shrinks, anything which is a pi shell shrinks, and it goes all the way down to its underlying wave function. So quantum mechanics shows us that a particle has a wave function. So there's a duality there. There's the wave, and then there's the particle. Now, when a particle is large, like an atom, its wave function is small. We characterize that mathematically in the following way. We say it's Planck's constant divided by the momentum. And so in very simple terms, if you think in terms of pi shells, uh, uh, the wavelength of the yellow or the C pi shell is different than the wavelength of the B pi shell. So the B pi shell is smaller, therefore it has higher momentum, therefore its wavelength should be shorter. So let me just double check that. Yeah, so if we look at this formula here, mv is larger divided by h, so the wavelength is shorter. So we can imagine as we move faster, the wavelength gets shorter. Okay, so that's how a pi shell goes from being very large to very small, and then you end up with these crested wave functions. Now there is the issue of how does a wave form a pi shell? How do you go from this form to this form? Okay, so let's recap on the definition of a pi shell, or an atom, or a particle in pi space theory. It's very simple. The way we do it in pi space is we say it's a pi shell, and it has area 4 pi r squared. But the one we focus on in pi space is what's called the square rule, which is pi times d squared, right? D being the diameter. So if you know the diameter of a particle or an atom, what I call a pi shell, or even a planet, you can approximate its area by multiplying by the constant pi. So that's what's formed from in the pi space theory. The wave functions form this object. So how do you go from a quantum a quantum wave function to to a to a pi shell in pi space. How does that work? So let's take a look at quantum theory as it currently exists. Uh, at the moment in quantum theory, um, we focus on the wave function, and the wave function represents what are called amplitudes. And if we want to calculate the probability that something will appear, we have to square the amplitudes. Okay, so I'm going to give you a very simple proof of why you need to square the amplitudes um, to get the probability, and then you how you figure out where the pi shell is going to appear, or the particle is going to appear, and why it works the way it does according to pi space, which is a theory. So the first thing is that a particle, as I've already shown you, has a diameter and it has an area. And as I've shown in the previous work, the relativistic work, the area maps to the energy of the object, and that's why E is equal to mc squared. The full version in pi space is E is equal to m times pi times c squared. You just add the constant pi. So when you create a particle from a wave in pi space using the pi space theory, you have to square the diameter, right? You have to square the diameter, and you have to multiply it by the constant pi. Now the important thing to realize here is that that the pi is very important. There are many physicists who talk about this constant pi appearing everywhere, and they say that it's just a constant. Now, in the pi space theory, the pi is not just a constant. I'll explain the reason why it's there according to the pi space theory. Right? So let's focus on the two sides of the formula. There's pi and there's the d squared. Now, if we map this idea to the quantum world, what you get is a wave function, which is the underlying mechanism for the probability amplitudes, as they're called, and these amplitudes combine to make either simple standing waves, or ones that move, or ones that have an unusual shape. But they can be added up together. I'll do a lecture on how you add them up and how it's just like pi space. But for the moment, let's take the simplest example. You have an amplitude, and it essentially has a peak here in positive space, and it has another trough here in negative space, and it has a position here where it has no value. So this is its maximum. This is its maximum value at the amplitude. It goes down and then it goes back up, and that's one wave, right? Now this is all pretty well known in quantum mechanics. Basically, this is one of the building blocks of quantum mechanics, where you work on the wave function, which is just amplitudes. And then the really interesting part about this is that when there was a huge debate between the Schrodinger Einstein camp and the side of the camp which was based on more the statistical side, which was to do with matrices and the other kind of way of presenting quantum mechanics, that Schrodinger came up with this equation which is called the Schrodinger wave equation, and this is foundational in mapping a object from an amplitude into a particle. But the thing is that when Schrodinger came up with this wave viewpoint, the statistical camp, Heisenberg and his group, they came up with this idea that the wave function just represents the amplitude of the event. and it's not tremendously intuitive, and this causes huge confusion, I think, because it's not tremendously intuitive what this amplitude is. I mean, it works, but a lot of people just don't get it. So you have this amplitude, and what the statistical side of the camp said, Heisenberg and his group said, was that you must square the amplitude in order to get the probability, right? You must square the amplitude to get the probability, right? So that's just the rule they came up with. Nobody really, they knew this was true because statistically that's the way it worked out. So you square the amplitude to get the probability, and then that's just the probability that a particle can appear somewhere. It's not that it will appear somewhere. And they said that you must sum up the probabilities and you must get one. So in other words, you must get up here at the top amplitude part here in order for it to have a high chance that it will appear in your reality. So there's three things. There's the amplitude, which is this wave function that represents this this chance of something appearing, but the chance is the squaring of the amplitude, and then the waves themselves can combine, and and then you get the object potentially appearing in a location. So let's map that idea to pi space. So if you look at the formula for pi space, just for a pi shell, the formula is really simple. I don't think it could be more simple. It's pi times d squared, right? So let's map quantum mechanics to pi space. Real simple. An observable particle in pi space is defined by pi times d squared, okay? D being the diameter. Now, if you map the amplitude to the potential diameter, what you get is a very simple formula, which is pi times the amplitude squared, right? So this here is the statistical analysis part. The diameter is replaced by the amplitude, right? And you must square it in order for it to form an observable. Now, the one thing that isn't here, that is part of, so this is your observable particle rule. This is quantum mechanics here. It's the amplitude squared, but it's just the probability. That should really say probability. The probability of the amplitude being squared, right? Now here's the really important part, and you must not think this is trivial, and it can appear trivial. Basically, the pi is really important. So what is the purpose of pi? That's really more the fundamental question here. The function of pi is what happens when a object you have this is the probability part here, the amplitude squared, and then this is the fact that the particle appeared, all right? So this is the appearance of the particle, and this is the probability of it appearing. So in other words, if you have an observable, you must combine with pi, right? So this is a very simple proof of why something appears in our reality and what the constituent components are. This is the amplitude squared, right? Which eventually becomes the diameter of the particle. And in simple particles, that's quite small. And then you have pi. So what this is saying is that in order for something to appear in our reality, and to actually manifest itself in our reality, when it's chosen, when it appears, and this is the part of quantum mechanics that's very confusing, it's that you can calculate where something's going to appear in terms of its probability, but you cannot exactly say at what exact point. The question is, what mechanism is choosing that a particle will appear in a particular position? And the answer is that at the moment we don't know, and it's a probability distribution function. But in pi space, it's called out what's choosing it. What's choosing it is pi. Now you might say that's just a constant, but it isn't. What it is all matter that exists in our reality is existing inside a probability density function, right? Which randomly distributes probabilities over discrete spaces. So if you take a look at the constant pi and you look at the digits of the constant pi, let's say you run up 1,000,000 digits of the constant pi, you will notice that in that sequence of digits, that all the digits will be equally but randomly distributed through that sequence. So in other words, what you get is you get if you have 0 to 9, you will get 0. If you have 1,000,000 and you have 10 base 10, you'll get 10. You will get 100. You will get say 100,000 zeros, 100,000 ones, 100,000 twos, 100,000 threes, 100,000 fours, and so on. They will be randomly but evenly distributed through 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 that sequence, just like as if you were tossing a coin or throwing a die. Pi is doing that. So what this is telling you is that we are inside a probability distribution function. That's actually what is missing from quantum mechanics at the moment, a probability distribution function. But the best we can do is to describe the probabilities. What we're doing is we calculate the probability of an event, and then we say we don't know exactly which object is going to appear where and when, but we do know that if we run it enough times, we get an even distribution in that space, and that's what pi is doing. So it's actually deceptively simple. That's what pi is doing. Now this is not a field. This is a constant, but this is an indicator that the probability distribution function of our reality is a pi. So the way we describe that in pi space is it's like being inside a field, a probability distribution field. And when something binds to our reality, like a particle physically manifests itself in our reality, it has bound to this. This part is the quantum part, which is the amplitude, which is this wave function here. And then the squaring of it is the piece that the statistical guys worked out that needed to be done. This is the forming of the diameter. And then the third piece that's just the probability. This is you binding. So I think a better way to describe quantum mechanics is that a particle needs to bind with our reality in order to become observable. It's like a protocol. And when you bind with our reality in a particle terms, you'll get the constant pi, right? This is without pi, it's a probability, and when it's bound to our reality, pi is there. Okay, so that's a very simple proof for why things why you need amplitudes, why you need to square them, and what the meaning of the constant pi is. It's a probability distribution function. I will talk maybe in another lecture about this probability distribution function. So what we are is we're inside a probability distribution function, which is pi based, and we're describing everything inside that probability distribution function. The best we can do right now with the current math we have is to talk about probabilities. Now if we were to be outside of this probability distribution function, this should be a function. This should be a function where you pass in the wave function a position and a time, and that would be the more general solution. I don't have one right now for pi space, but I just want to give you an idea of currently how these spheres manifest themselves in our reality. So that's what's required for this to manifest itself in our reality. This could be an electron, it could be a hydrogen atom, it could be an entire planet made of atoms. But for the purposes of the quantum world, we're talking about maybe the forming a electron particle from a electron wave. So that very simple formula, pi times d squared, can describe quantum mechanics and how you bind to our reality. It's deceptively simple. I will talk some more in later lectures about Euler's identity, and I'll talk about the Schrodinger wave equation and how that all can be described in pi space. I would say reasonably simply. It's not very simple, but it's reasonably simple. Take care.